History Museum tells the story of our planet, from evolution to changing climates. Today in our story is entering a new and unprecedented chapter. Human activity is driving rapid changes in our climate, warming the atmosphere, causing the sea to rise. In this short video, we'll cover how scientists observe and understand these changes, from satellites orbiting above Earth to mathematical equations describing sea level change.
And to start off, we will travel to the Arctic forefront of climate change, the Barents Sea. The Arctic's average temperature has already risen at a rate of 3 times the global average, warming faster than any region on Earth. While Arctic glaciers and ice caps represent only 25% of the world's land ice area, meltwater from these sources account for 35% of the current global sea level rise. Let's start off by describing the difference between sea ice and land ice. Land ice is several meters thick, and when it melts, it directly contributes to sea level rise. When sea ice melts, it affects the ocean's albedo, allowing waters to absorb more solar radiation and further warming it. Summer Arctic sea ice extent is shrinking by 13% per decade, and the sea ice cover continues to be thinner. The decline in sea ice thickness and extent, along with the changes in the timing of ice melt, are putting animals that are particularly ice dependent, such as walruses, at risk. Sea ice plays a critical role in the Earth's climate system, helping the planet cool. As the Earth diminishes, the darker ocean beneath absorbs more sunlight and affects and reduces the Arctic's effectiveness as a global cooling system. Scientists monitor ice and sea level change using several methods: tide gauges along coastlines, gravimetry missions like GRACE that detect changes in the Earth's gravity from melting ice, and satellite altimetry, which measures surface height from space. Altimetry works by sending microwave radar pulses from a satellite to the Earth's surface and measuring the time it takes for the signal to return. By combining this with the satellite's orbit data, scientists can determine surface elevation to within a few centimeters. Over the ocean, this gives the sea surface height, and over ice, the radar penetrates the snow layer and reflects off the ice surface, allowing estimates of the ice thickness and volume change. However, using radar in these conditions can be complicated. Surface roughness and sea ice can distort the radar signal, making it difficult to distinguish ice, air, and water. To correct for these effects, scientists use multiple radar frequencies. Modern altimetry missions include ESA's Cryosat-2 and NASA's JASON series. Here is a graph showing the global mean sea level record. This dataset represents normalized global mean sea level, corrected for tides, atmospheric pressure, and instrumental drift. Now let's sonify this data and see what it gives us. To understand the drivers of sea level change, we can use the sea level equation, shown here, by S equals n minus u. S represents the relative sea level change at a specific location, defined as the displacement of the ocean's surface relative to the sea floor or the solid earth crust. N represents the change in sea surface height, which includes the eustatic components, which includes water volume changes such as added meltwater and thermospheric expansion due to ocean warming. U represents the vertical movement or isostatic adjustment of the solid Earth. This could be due to overlying mass loads, which could be from the glacial isostatic adjustment. Thank you for watching, I hope you enjoyed.